Okay, so good afternoon, everyone. My name is Sanchit, and our group is me, Samadeep, Aryan, Karan, and Tanuj and Vikas. Tanuj and Vikas can't be here because they're given an exam right now. But we thought of preparing this paper of ultra long spin coherence in isotopically engineered diamond. This isotopically engineered diamond, I think, here is the key phrase because these guys have developed this new technique of developing these noise-free diamonds, which I would like to expand a bit more on. So, how these in these diamonds we see really long coherence times compared to the other diamonds which are prepared, and yeah, that's pretty much what the paper covers. But um, it's really fantastic as to how these people developed this. So the goal is to create a quiet diamond. Now, what do you mean by a quiet diamond? So, as we know that we have when we are forming diamonds, we have NV centers in them, and carbon is found in like many of its natural isotopes. So C12, C13. Now, so the C13 isotope of the carbon atom has this extra spin, which also contributes to the noise, and which is like really high noise when it comes to like the measurements. And we basically want to remove this C13 isotope from our diamond structure. And so what these people came up with is that they were they wanted to grow a diamond sample without this, with at least the minimum of this 13C isotope. So they used this method of they started with a carbon substrate which was aligned at a 100 Miller indices, plane indices, and then they grew the the diamond over it with this with the CVD technique of the methane gas, and they use some sort of isotopic methane gas which which chemically lacks the 13C isotope overall. And the intrinsic nitrogen within the chamber combines in the vacancies within these positions to form these NV sites. And with that, we basically get a diamond structure. And with the lack of these 13C isotopes in the structure, we remove the extra noise which is contributed by this 13C, and the other, like the extra dipolar interaction due to these 13C isotopes and within the lattice is also removed to a great extent. So yeah, so they also looked into the FID profiles after they created the substrate. So what they basically did is that within an external magnetic field, they first initialize the system by putting a green pulse laser in it, and then they apply a radio pulse of pi by 2, and then for a time tau they let the system evolve freely. And after that time tau, they again apply a pi by 2 pulse to get it back to the initial state. And this is the intensity profile with the time tau over here. So this one here is for the normally engineered diamond which has the 13C isotope, and this one is for the one which doesn't. So as you can see here, it decoheres it decoheres pretty much within 5 microseconds, I think. Yeah. But in case of the other one, which lacks 13C, I won't say lack, but it has 13C in a very minute quantity. The FID over here has these significant oscillations over here like this. And when you take a Fourier transform of this whole thing, you get this for the normal lattice, for the normal diamond lattice, you get this kind of a structure, which is basically for this frequency. And in case of this, you get a hyperfine structure like this. And these two over here are what correspond to the NV centers of the asteroid. And the middle peak, which you see here, is what in the paper they claim to be from a 13C isotope, which is distantly located. But what over here you should notice is that how the line width is insanely minimized over here. You can see it's like 210 kilohertz, and here it's 55 kilohertz, which will give you a great coherence time. So they also perform a magnetometry on the sample, and so it's similar. They give these are two magnetic field pulses. One is a sine and one is a rectangular pulse, and they start with a pi by 2 pulse to give a radio pulse for the system to evolve within time tau, and then they again apply a pi pulse to get it back to the system, and it evolves within this sine curve of a magnetic field. And over here, it's a similar thing. They just do it with a square pulse. So over here, you can see that you get this oscillation kind of thing over here. That is the intensity profile with the evolution time tau. And this basically, you can map this. There was a formula in the paper, phi and the magnetic field B. So you get these kinds of oscillations, and if you do a wavelet transform, so you basically reproduce the pulses that you give. So basically, what they wanted to show here is that how sensitive the NV center dipole is to the external magnetic field, because when you're transforming the experimental signal using a wavelet transformation, you get back a sine wave and a square wave, which you initially sent initially. So that's another example how sensitive this system is without the 13C isotope. And the sensitivity depends on 1 by root over of tau, which is where tau is your evolution time. Now, the most important aspect of the paper, so can't get it in the middle. So yeah. So yeah, the most important aspect of this paper is this. What they did here is that they did a similar thing. They they first initialize the system, then give a pi pulse and let the system evolve for some time tau, and then they give a pi pulse, and then they let it again evolve for system tau, and they basically see how this amplitude basically go how the trend of the amplitude with the evolution time tau, and they fit it with this exponential decay function, where you can basically get this T2, which is the coherence time. So initially here the tau is limited by the tau is always lesser than the coherence time. So here they wanted to measure the coherence time, and you can see it comes very nice. It's like 1.82.06 milliseconds, which is which is great if you compare it to the ones which have the 13C isotope. So yeah, that's pretty much all that the paper covers, and it basically gives you a new set of samples which have this more which has this longer coherence time, so it would be able to, and less decoherence time, so it can store the quantum information for a longer period of time if you use this for its applications in quantum computers, like in quantum information basically. So yeah, that was all. Thank you for listening, and I would like to thank my peers who helped me prepare, they prepared the slides. So yeah, that's all.
Nicely timed presentation.
Perhaps when you come back to the very
First slide.
no, can you re-explain a little bit what the curve that will be after when you apply the second slide, the slide later?
This one?
No, just following one with the magnetic, the sinusoidal magnetic field.
This one?
Yes.
So
we see a fringe period, a period.
this one?
Yes,
Yeah. So
does it change?
because like when you increase the magnetic field, so it goes from here to here, so the phase basically squeezes, so you get a lot of rapid oscillations in the middle, and then it spreads out at the end. So yeah.
And then it's content when you apply the square wave.
Right. So it's like, yeah, and then there's a certain oscillation, and then there's a little bit of uplift here which I don't understand really, but yeah. Thank you, sir.